All right, guys, so I just wanted to take a little bit of time to go ahead and talk through these questions with you, just in case that would be helpful for you. If you don't want to watch the video, then just look at the PDF that I've also attached to the assignment, all right? So we got a 65 kilogram skier starting at rest from his frictionless slope. You're going to go down the slope and then up off the jump, and at this point he's going to fly off, right? The question, of course, is with what speed does the skier leave the jump? So that's what it's asking right here. This is going to be our final point. It's probably makes sense that this right here is going to be our initial point. That's good to recognize. If you can get that from the question, starting point, ending point, that'll be helpful to you. We are considering the skier Earth system, which means that we're paying attention to the gravitational potential energy because it's the skier Earth system, and then any other forces that are there. So the first thing it asks is to draw a free body diagram on the skier at the top of the slope. So here's the skier right here. We've got the force of gravity, which is pulling down, and then we've got the normal force of the slope, which is kind of pushing up to the right, kind of like that, right? And that's it. No other forces. Even if he was moving, it does say frictionless, which means he's just going to slide along, no other forces. All right? Letter B says, are kinematics, Newton's laws, a valid way to solve this question? Why or why not? And the answer, of course, is no, because the acceleration is changing, right? As we go down the slope, right here, you've got the force this way. Let me go ahead and go back. So the normal force is this way and gravity is this way. But when I come down here, the normal force is up that way and gravity is this way. And as I get over here, the normal force is now upwards and gravity is this way. So the net force, adding those together, the net force is always changing. And if the net force is always changing, because force equals mass times acceleration, it means that the acceleration is changing. And if the acceleration is changing, then we can't use kinematics. It also makes it very difficult to use Newton's laws because Newton's laws has us do the sum of the forces, and if the forces are always changing, then we have a different acceleration at every point. So no, we aren't going to use kinematics or Newton's laws at this point. Letter C says, can we use conservation of momentum to solve this question? And again, the answer is no, because the one restriction for conservation of momentum was no external forces, right? And there definitely are external forces here, right? You've got the normal force and gravity that are both causing changes in the object's momentum. So we're gonna, no, you can't use conservation of momentum, because that is the requirement that there are no external forces, but there are external forces. So I should probably clarify that. Otherwise, that will be confusing later. So there are external forces that are unbalanced, right? Okay. Letter D. We know that gravity, the force of gravity, is a conservative force, so that allows energy conservation. This is referring to part A here, where we drew our forces. So gravity, remember gravity was in all of the pictures up here, all of our force diagrams up on the slope. So that's a conservational force, that's okay. But why do we ignore the normal force? Because we did say that we can't have other external forces that are non-conservative, and normal forces are not conservative forces. Well, hopefully you remember our discussion from class that the normal force here is perpendicular. And one of the things we said in class is that perpendicular forces don't, that's a C, don't do work. And so that means work equals 0, and remember that work is also defined as the change in energy, which means that the overall change in mechanical energy, right? We've been referring to this as energy, but the change in mechanical energy, there's no work being done. All right, on to letter E. In the initial position, what types of mechanical energy are present? Well, he's starting from rest, so definitely not kinetic. And there's no springs or stretchy cables or anything like that, so no elastic potential. We do know that you can define your zero height to be anywhere, but it probably isn't going to be at the top. So I think it's pretty safe to say that there is going to be a gravitational potential energy, right? In letter F, it says in the final position, what types of mechanical energy are present? Well, obviously there's no elastic potential. Kinetic, for sure there is, right? Definitely kinetic because it's going to go flying off the edge. Gravitational potential is going to depend on how you define your zero, all right? And let me just kind of demonstrate that. If in my original drawing, if I define this to be zero, the very, very bottom, then yes, there's going to be some gravitational potential energy there because the height is 10. A much easier way to address this question, because I don't really need to know anything about the bottom isn't actually important here, is that you can actually do this. You can identify this as being height equals 0. Now, if you define that to be height equals 0, that means that right now, at the very end of the ski jump, the height is 0, and so gravitational potential energy is 0. That's going to simplify the question for you. Completely up to you how you do it. Some people like to just say, you know what, it's easier for me just to make the bottom 0 every time, and then you just make the bottom 0 every time. And other people say, well, I want to simplify the equation. So that's completely up to you. I'm going to go ahead and say that there's kinetic energy. This is height 0, and so there's no gravitational potential energy there. All right, moving on to letter G, it says use the general conservation of energy equation to write a simplified equation for this scenario. So remember, that's where we say the change in energy, again we're talking about mechanical energy here, is equal to the change in kinetic plus the change in gravitational potential plus the change in the elastic potential. And of course, we already said that the change in energy was 0. That came from up here in letter D, right? That's where this E0 came from. We already said that there's no electric potential, so that one's going to be 0. Elastic potential, so that's going to be 0. And so we can go ahead and start rewriting. We can say that 0 is equal to, and then the change is always final minus initial plus gravitational final minus gravitational initial. And so we can go ahead and we can cancel out the things that are 0. We know initially there's no kinetic energy, so we'll take out the kinetic initial. And we know finally there's no gravitational potential, so we'll take out that. And so we're left with, and at this point we can put in 1/2 mv squared final, and then we can put in that minus mgh initial. And at this point, we're ready to move on to letter H, where it says put in values and calculate the speed of the skier. So we get to go 0 equals 1/2 times the mass, which is 65, times the velocity, which is what we're looking for, and then minus the mass 65 times gravity, which is 10, acceleration of gravity. And remember, we talked about that it's the magnitude when we're talking about gravitational potential energy. And then the height, in my case, the initial height is only going to be 40, right? Because I only want the height to that point that I defined as 0, and there's 10 below. So this is 10 down here, so that means the initial height above that 0 point is actually going to be 40. All right? And so at this point, I can start plugging into my calculator. And I'm going to work through it a little bit just because I know there are a couple of people that are still having a little bit of a hard time getting the numbers to work out right. So 1/2 times 65 is going to be 32.5 times VF squared. And then I'm going to go 65 times 10 times 40. And that is 2,600, or sorry, 26,000. So that should be a minus. Okay, we're going to move the 2,600 to the other side and then divide by 32.5. And that gives us 800. So now we have 800 equals VF squared. So I added the 26,000 and then I divided by the 32.5. And now I'm ready to square root it. And when I square root it, that should give me then the final answer. All right? and I get that the final speed is about 28.3 meters per second. Ta-da! That's question number 1. All right, let's move on to question number 2. And here we go. So we now have a 2.5 kilogram block starting from rest at the top of the frictionless ramp. Again, frictionless. Okay, it slides down the ramp and then across a frictionless surface. So you can see that it's going to go down the ramp, and then it gets down here, and then it's going to slide across that surface, and then eventually it's going to collide with this little spring down here that's going to bring it to rest, and then actually push it back up in the opposite direction. All right. One thing to recognize is that if it did do that, it would slide down, hit the spring, bounce back, and go back up to the exact same height, just like the pendulum does, right? As long as there's no friction and no energy being lost, then that's what would happen. It would go right back up to the same height that it came from, which is kind of a neat idea. All right, so we're going to consider the block earth spring system. Of course, counting earth allows us to have the gravitational potential energy, and including the spring allows us to have the elastic potential energy. So we're including that whole system here, and it gives us the spring constant, all right? So the first thing that it wants us to do, of course, is to draw a free body diagram on the block as it slides down the ramp. So as it goes down the ramp, here it is. This looks very familiar. We've got a force of gravity going down, and we've got the normal force going up in this direction. It says, is kinematics or Newton's laws a valid way to calculate the speed of the block at the bottom of the ramp? Why or why not? Well, yes and no. Okay, in some ways it is. The acceleration is not changing, right? From this point here until we get to the bottom of the ramp, these forces stay the same. The net force is always the same. And if the net force is always the same, then the acceleration isn't changing, right? The acceleration is always the same. It does speed up, but it has a constant acceleration. So that's one thing to note, is that, yeah, that the acceleration is not changing. The problem here is that we can't calculate that acceleration because we know the height, but we don't actually know what angle this is. And without knowing the length of the side, there's no way to find the angle. Okay, so the acceleration is not changing. It's constant, but we can't find it without the angle. And that's because over here, right, we can't figure out what direction the normal force is in. What component of that is vertical to balance gravity, and what component of it is kind of in the other direction, the horizontal direction. And so that's not something that we're able to answer right now. And so is Newton's laws and kinematics a valid way to do it? It would be if I had a little more information. But unfortunately, I don't have the information, so I can't actually do it. So no. Letter C says, we know that force of gravity is a conservative force, so allows energy conservation, right? It's included in that gravitational potential energy. Why can we ignore the normal force of the ramp on the block? Again, it's because the normal force is perpendicular. And perpendicular forces, okay, this means perpendicular. In case you haven't got that in math class yet, perpendicular forces do not do work. So therefore, work is 0, and so is the change of energy. So we can use conservation of energy. That's something we should always double check before we do that conservation of energy. Is kinematics Newton's laws a valid way to calculate the compression of the spring? Now this one is a clear no. Okay, this one is a clear no because as the spring changes, the force of the spring changes, right? As the displacement of the spring changes, the force of the spring changes. That should kind of make sense. If you've ever played around with a bungee cord or a spring, the farther you push it or the farther you stretch it, the harder it is to stretch it, right? It gets more and more difficult because the force gets bigger and bigger. The force is changing depending on how far you compress it or how far you stretch it. And so as the displacement of the spring changes, the force changes, and of course, F equals ma, so the acceleration is not constant. All right, letter E. In the initial position at the top of the ramp, what types of mechanical energy are present? Hopefully you recognize that it starts from rest, so that's no kinetic energy. There's no elastic potential energy. Yes, there's a spring, but it hasn't been compressed yet. So the only thing we got there is gravitational potential energy. Letter F says in the final position at the bottom of the ramp. So we're talking about this position right here. Right here at the bottom of the ramp, before it hits the spring, what types of mechanical energy are present? Well, it's at the ground. I think we're pretty safe to say that the ground is height 0, so no gravitational potential. If it hasn't hit the spring yet, then there's no elastic potential either. Remember, the elastic potential comes when we compress or we stretch the spring and the energy is kind of stored in there until it's able to go back to its initial position. And so in that case, there's no elastic potential either. The only thing we have is the kinetic energy because it's obviously moving when it gets to the bottom of the ramp. That's it. Let's move on to letter G. So now we're going to use the conservation of energy equation. Again, delta E equals the change in kinetic plus the change in gravitational potential plus the change in elastic potential. This time there was no elastic potential. The kinetic energy, this was also 0 because there was no work being done. Remember, we talked about that in an earlier section. And so now we can rewrite it as 0 equals final minus initial. And then plus gravitational final minus gravitational potential energy initial. And we talked about how there was no initial kinetic energy because it was at rest, and no final gravitational potential energy because it was at the bottom where height was 0. And so we can now rewrite it as 1/2 mv squared final minus mgh initial. Now we're ready to go ahead and put the values in. And when we put the values in, we should now be able to calculate the speed when it gets to the bottom of the ramp. All right? So we go 0 equals 1/2 times 2.5 kilograms times that final velocity squared minus again 2.5 times 10 times the height, which was 2 meters. And we can now work through that. 1.25 VF squared and minus 50. 2.5 times 10 is 25 times 2 is 50. We're going to add the 50 to the other side and then divide by 1.25. And then, of course, after that, we will square root it. So we get the square root of 40, which means that that final velocity is equal to 6.32 meters per second. There we go. We got the speed at the bottom of the ramp. Now it continues. It says there are many ways to calculate the compression of the spring, but we will consider the initial point at the top of the ramp and the final point when the spring is at maximum compression. Why can we do this? Well, what are the forces? You got the force of gravity is always conservative. At some point, we're going to have the force of the spring, which is always conservative. As long as I'm looking at the spring block system, right? Just like gravity is conservative if I'm looking at the spring, the block earth system. So I'm looking at the block earth spring system all together, so those are both always conservative. And the only other force that appears here is the normal force, which in this case is always, always perpendicular. And so therefore, we're able to use, we can start with the object at the very top, and we can end with the object at the very end, right? And so in letter J, it says, in the final position when the spring is at maximum compression, what types of mechanical energy are present? Well, we've got kinetic, gravitational, and elastic. There's no kinetic energy. We talked about that in class. Remember, when it gets to the maximum compression, that's when it slows down and stops just for that instant before it springs back in the other direction. So we're looking for that instant when the kinetic energy is 0, when the speed is 0. There's no gravitational because it's still at that 0 height. So therefore, the only type of energy we have present is the elastic potential. Now it says use the conservation of energy equation to write a simplified equation for the, this should be block, sorry, as it reaches the bottom of the ramp. Adding zeros where appropriate. So again, change in mechanical energy is equal to change in kinetic energy plus the change in gravitational potential energy plus the change in elastic energy. Now, remember at the very beginning, we had said that kinetic was 0, elastic was 0, and we did have gravitational potential at the very beginning, when the block was up at the top of the ramp. This is from a previous section on the previous page, right? You can go back and look at it if you want. Look back at your notes. And so we can start writing this. We do know that this is going to be 0 because of what we talked about here, conservative forces and the perpendicular force. We know, look at this, no kinetic energy at the top of the ramp and no kinetic energy when it hits the spring. That means we get to take out kinetic energy. All right, so we're ready to start rewriting a little bit. So we're going to go 0 equals gravitational potential final minus gravitational potential initial plus elastic potential final minus elastic potential initial. And of course, we can take out the final gravitational potential energy, and we can take out the initial elastic, right? Because there was no compression there initially. And then we talked about no gravitational at the end. And so we're now ready to write our equation. 0 equals negative mgh initial plus 1/2 kx squared final. Remember where x is the compression of the block, and that's what we're going to look for. It says there's many ways to calculate the compression of the spring. That's what we're looking for, the compression of the spring. All right, now it says put in values and calculate. I made a mistake here. This should not say the speed of the block. I'll correct it on the worksheet. It should say the compression of the spring as it reaches the bottom of the ramp. The block reaches the bottom of the ramp. And so we're now going to put the numbers into our equation there. So we go 0 equals, the mass again was 2.5. So we'll go negative 2.5. This is negative because of this right here, right? So it is negative. It's not because of negative potential energy. It's just because there was a change there. So that's negative. Gravity is still 10, and the height was 2 meters. And then we go plus 1/2 k was 200. That was given on the previous page. And sorry, 250. If I remember right. So 250. And then times x, that compression squared. And that's what we're going to solve for. And so we can do the solving. This time I'll let you do the solving. And when we work it out, you should hopefully get that the compression of the spring is 0.63 meters, about 63 centimeters. All right, and that's it, my friends. That's the answer to letter L. All right, now the last question says, suggest another way you could have used conservation of energy to calculate the compression of the spring. Well, we could have used the information from H, right? We knew the kinetic energy at the bottom of the ramp, right? When there was no gravitational and no elastic potential, also 0, sorry. So we knew that. And then you could use, just like we just did, then you could use the elastic potential at the end, because we know that gravitational potential is 0 and kinetic is also 0 at the very end. And so if we use those two in conservation of energy, you can also calculate the displacement that way. And the equation would simplify to 0 equals 1/2 kx squared minus 1/2 mv squared initial. All right, and you can go through. You can show that process if you'd like. That, I think, is less important. What is important is that you recognize that you can use the point at the bottom of the ramp and then the spring instead of starting at the beginning. But I wanted to make sure that you understood that you can start at the beginning as well, as long as, like we showed in letter I there, remember, as long as we can show that the forces are always conservative and the other forces are not doing work, then you can use conservation of energy over any range of time. All right, that's it for tonight. Thank you guys. I hope that was helpful, and I'll get this posted for you right now.